Okay, so we defined what is the covariance and what is the correlation coefficient. We learned how we calculate them, and the idea is the covariance captures the sign, the direction of the relationship, and the correlation coefficient is a standardized covariance to capture the direction and the strength at the same time. And now we are going to extend the analysis to more than two variables. Suppose that we have five macroeconomic variables, like over a long time period. So the five variables are GDP growth rate, industrial production growth rate, and CPI, consumer price index inflation rate, unemployment rate, and 10-year treasury bill rate, interest rate, right? So they are pretty common and some of the most important variables in macroeconomic analysis. So, and it is important to think about those variables at the same time, right? Because they are intercorrelated. So we would like to use data. We have data on them. Like we have the data from 1962 first quarter up to 2015 like last quarter, so fourth quarter. So the number of observations is 216, right? So we have more than 200 quarterly data on five variables: real GDP growth, industrial growth, inflation, unemployment rate, interest rate. The problem is when we have five variables, covariance and correlation coefficient does not work anymore, right? So covariance and correlation coefficients are only for two variables. So when you have three variables or more, you have to calculate the covariance pairwise for each pair, right? So you can calculate, like for example, covariance between these two variables and these two variables or these two variables. That's what you have to do when you have multiple variables. So that's what we are going to do here. We are going to calculate the covariance for each pair of variables. And then we will have a table like this, right? So if you choose GDP growth rate and GDP growth rate, covariance between GDP and GDP is the variance of GDP, right? I told you in the previous video, I told you that we learned that the covariance is a generalization of the variance. So the covariance of GDP and like with itself is its variance. Also, you can calculate GDP growth rate, like covariance between the GDP growth rate and industrial production growth rate. That is 7.66. And inflation and GDP is here. Unemployment rate and GDP is here. Treasury rate and GDP is here. So you can think about the pair like for each column and row. If you choose a column and a row, then you get a pair of variables and you calculate their covariance. The upper side is empty because, like for example, if you're interested in unemployment rate and inflation rate, instead of looking at here, you have to look at here. Unemployment, inflation is empty, but inflation and unemployment is 0.48. So basically there are only 10 pairs of variable, not like this many pairs of variables you can find, and the order does not matter. Covariance between x and y equals covariance between y and x. So there is no duplicates. It does not duplicate the covariances. And Excel has a simple way to calculate those table matrix, right? So go to Data tab, and let me move my face here. And I have data analysis button here. Because in case you don't see this button, you have to install an add-in. So to calculate add-in, you need to go to options and install add-in here, analysis toolpack. I installed analysis toolpack, and in case you don't have that, then if you see analysis toolpack under inactive applications, then you can install that by clicking here. Okay. Anyhow, I already installed it, so I'll click it, data analysis, and I will click covariance. Covariance. Then you have to choose input range. I will simply choose 5 variables, 5 columns at the same time, grouped by columns. And the first row is labels. So I will just click OK. Then you get 5 by 5 matrix. Same matrix you see on the slides, right? So exactly this tells you the covariance between a pair of variables, right? Then, first, the diagonal terms are variances. For example, variance of GDP 11.33 is variance of GDP, and say 21.45 is variance of industrial production. Let's check that. I can directly calculate sample variance of GDP is 11.3 increase sample 11.38395. That is no, it's so then it must be population formula, right? Population variance is 11.3312. So this is population variance, right? Population variance, not the sample variance, but basically they are similar. And by this way, you can check the variances are. If you calculate other variables variances, you get these numbers: 21.5, 8.26, 2.57, 7.79. They are those diagonal numbers, right? Exactly, you see those diagonal numbers. They are variances. Variances of each variable go to the diagonal entries. But the non-diagonal terms are covariances. Covariance between two different variables. Okay, so as I said, you make a pair by choosing column and column and row. So then you find the covariance. Then but remember, the covariance only gives you the direction. The size does not tell you anything, right? So let's interpret that. GDP has a positive covariance, positive relationship with industrial production and treasury bill rates, which is expected, right? So when the economy grows faster, and then of course industrial production increases, and also the interest rate will increase, right? Because you expect better growth rate. But the GDP growth rate has a negative relationship with inflation rate and the unemployment rate. So the negative relationship with unemployment rate is natural. If the economy is in boom, then more people will be employed, so unemployment rate will be lower. But the problem is the inflation. So we expect when the economy is growing quickly faster, then inflation will also go up quickly, right? The price index will increase with the economy. But somehow the inflation is negatively correlated with the GDP growth rate. This is a puzzle in macroeconomics, or like decades ago, many macroeconomists tried to explain why the GDP growth rate is negatively correlated with inflation rates. I will explain that in a minute, right? So anyhow, this is how we use the covariance matrix. But like as you may have expected, we would like to learn the strength of the relationship. Like, so these numbers, the absolute numbers of the absolute values of the covariance do not imply the strength. So we cannot compare the magnitudes, the strength. For example, among those positively correlated variables with GDP, industrial production has a covariance of 7, and treasury bill rate has a covariance of 0.1. But it does not imply IP has a stronger correlation with GDP than the treasury bill rate. You cannot compare the absolute values. That's a limitation of the covariance. So we are going to turn the covariances into correlation coefficients, right? We can do that easily on Excel by, again, going to Data tab and click Data Analysis here, and choose Correlation, and then click OK, and follow the same thing. Choose Data and labels in the first row. Click OK. Then you get another table, 5 by 5 table with correlation coefficients. And as you see, all the numbers are between plus minus 1. Okay, so these are correlation coefficients. Okay, right? So you can I skipped this. You can calculate the correlation coefficient actually using the covariance and the variances, because the variance, square root of the variance is standard deviation. So use that to standardize the covariance. Then you will get, you can use this formula, right? You have covariance and you have variance from the data, from the matrix. So actually you can calculate correlation coefficients directly from the matrix, but we already did it on Excel, right? So we get this new matrix which contains the correlation coefficients, okay? So in this case, but the diagonal terms have no meaning, because think about this. This 1 means the correlation coefficient between GDP and GDP itself, which is of course perfect correlation because they are the same variable, right? So no matter, like, of course, correlation with myself is 1, right? Perfectly correlated. But now, like, but also the signs are preserved. So if covariance is positive, correlation coefficient is also positive. Vice versa. If it's negative, then of course correlation coefficient is negative. So, and now, but what we can do more is the comparison of strength of the relationship. So GDP and IP growth rate has a strength of 0.49, but which is greater than the strength between GDP and treasury bill rates, which is only 0.02. So the strength can be compared across different pairs of variables, right? So you can tell the direction and the strength at the same time from this matrix, right? So this is also another useful matrix we can use when you have multiple variables. For example, which pair has the strongest negative correlation relationship, right? So easy to answer. Strongest negative correlation means you need to find a number that is closest to -1, right? So there are many minus negative relationships, and I think this is the strongest, like the smallest, closest to -1. So unemployment rate and industrial production has strongest negative relationship. Okay, that's how we utilize this matrix, right? So, okay, this is like a generalization of covariance and correlation coefficients to multiple variables. Basically, there is nothing new. You just have to do multiple pairs together. So in the end, actually, covariance and correlation coefficients are not ideal when you have multiple variables. Still, you may use this kind of matrix, but I recommend you to use regression model we are going to learn in the next chapter. Okay, so thank you very much for watching, and I will see you in the next video.